Welcome to Easy BTech, your guidance for BTech and beyond your career. It's a platform where you can learn the subject very easily. My name is G. Sampath. I'm going to teach the subject VLSI. Last class, we discussed the IC technology, IC technology. In IC, VLSI is in IC technology. So VLSI is fourth generation IC. It is a fourth generation IC, and we also discussed the MOS transistor types. MOS transistor, we are seeing different types of MOS transistors: NMOS, PMOS, CMOS, and BiCMOS. We also discussed NMOS is classified into enhancement mode, and depletion mode. And PMOS is also enhancement mode and depletion mode. So these are the introduction I gave you. What is NMOS? What is PMOS? And enhancement mode transistor, depletion mode transistor. In enhancement mode transistor, no channel existed. By applying external gate voltage, we apply external gate voltage. In depletion mode, no need to apply external voltage. No external gate voltage. No external gate voltage. Okay. So NMOS logic 1 applied in NMOS, logic 1 or positive 5 volts we are applying. So it is on transistor. In PMOS, if you are applying in NMOS enhancement, in enhancement of PMOS, we apply logic 0, or we can say negative voltage. So minus 5 volts. Gate with respect to source. The transistor is on. Okay. And also we discussed NMOS enhancement transistor action. NMOS enhancement transistor action. So this is we discussed by using a design pattern. Let us see in a symbol representation, in transistor symbol representation. So how it will be work in a circuit. Let us see in a circuit. Let us say this is a VGS we are applying, gate to source voltage, and this is a VDD, and this is a VSS. So the terminals are here: gate, drain, and source. Okay, in enhancement, no need to apply external voltage. How it will be on? By applying external voltage, there is a channel formation and there is a current flow IDS. Effective gate voltage VGS is equal to positive volts or 5 volts, or we can say logic 1 we are applying. There is a channel formation between drain to source. There is a channel formation between drain to source and IDS flow. This IDS will flow and we can take the voltage is called VDS. The voltage is called VDS. So in enhancement, we are taking the two conditions: external gate voltage VGS minus VT, applied voltage VGS, required threshold voltage VT, then the voltage across this channel area is VGS minus VT is less than drain to source voltage. The condition is called non-saturation region. Non-saturation region. Non-saturation region, what happens? The channel is like inclined channel existed. Inclined channel existed. We call this, it is an inclined channel existed. Inclined channel existed. The second condition we discussed in the figure. So VGS minus VT is equal to VDS. So the way of the channel is depend on this external gate voltage and this VDS. Now flat channel existed. There is a flat channel existed. Here it is a flat channel existed from drain to source. It is called saturation region. Saturation region. So there are two conditions existed in enhancement mode transistor by applying VGS. So in PMOS enhancement, so exactly it is opposite. If you are applying negative 5 volts VGS and logic 0, so it is non-saturation and saturation. Only two conditions is existed in enhancement of NMOS transistor. Now let us see. Today we will discuss NMOS fabrication. NMOS NMOS fabrication process. There are 9 following steps for fabrication of NMOS transistor. NMOS transistor. So let us see. It is a basic transistor design. With the NMOS transistor design, we can design PMOS, we can design CMOS, and also BiCMOS. The first step in the fabrication process, take a part of silicon wafer. The dimensions are 75 to 150 millimeter diameter, 0.4 millimeter thickness, 0.4 millimeter thickness, and impurity concentration, p-type impurity added to this. P-type impurity added, it is 10 power 15 cube centimeter. 10 power 15 cube centimeter to 10 power 16 cube centimeter. So mostly used p-type impurity is boron. Boron impurity added to the silicon wafer impurity. And resistance 25 ohm centimeter to 2 ohm centimeter. This is the representation, the first designing process. Let us see the diagram. The diagram is, you can take a part of silicon 75 to 150 millimeter diameter, 0.4 millimeter thickness, and p-type impurity concentration, and mostly used boron. So it is a p-type substrate area. We can take a p-type substrate area formation. The first step is called as a p-type substrate area formation. So this is called p-type substrate area formation. P-type substrate area formation. Let us see the second one. SiO2 layer. SiO2 layer deposition on. The second step, SiO2 layer deposition on p-type substrate area. P-type substrate area. P-type substrate area. So it act as a protect to the dopants. P-type dopant protect to the dopants and barrier for the next layer. Barrier for the next layer. So SiO2 layer is deposition on p-type substrate area. It acts as a barrier for the next layer and protect to the dopants. Let us see this diagram. You see, this is a first step, p-type substrate area formation, and second one is SiO2 layer deposition. You see, SiO2 layer deposition. So this is a p-type substrate area. The first step, p-type impurity, boron impurity added, silicon wafer with p-type impurity added. Then second step is SiO2 layer deposition. So it is a protect for this below p-type dopants and barrier for the next layer. It acts as a barrier for the next layer. This is SiO2 layer deposition. SiO2 layer, it is a 1 micrometer thickness. 1 micrometer thickness. 1 micrometer thickness SiO2 layer deposition on this p-type substrate area. This p-type substrate area. P-type substrate area. Now the third one, photoresist layer deposition. Photoresist layer deposition on SiO2 layer. SiO2 layer. What is SiO2 layer? So it is silicon and added oxygen added to the silicon. So SiO2 layer, photoresist layer is deposition on SiO2 layer. So it is a photosensitive emulsion. Photosensitive emulsion coating to the wafer. Photosensitive emulsion to the wafer, silicon wafer. It is exposed to the UV rays. It is exposed to the UV rays. You see the students, photoresist layer is another layer deposition on SiO2 layer. You see this one, ma? The below one, the first one is a P-type substrate area. Then we are seeing this SiO2 layer. Okay, this is the second step. Now third step is photoresist layer is deposition. You see. So it is a designing process. In the examination also, you should draw this step by step and explain how the process is going on. You see, the first one is a P-type substrate area. The first step, P-type substrate area. Then SiO2 layer, 1 micrometer thickness SiO2 layer deposition on P-type substrate area. Then this is a photoresist layer. Photoresist layer is deposition on SiO2 layer. So it is used to expose to the UV rays in the mask processing. This is a photoresist layer. Photoresist layer. Photoresist layer is deposition on SiO2 layer. It is used to UV rays. It is used for exposure to the UV rays in the mask processing. Let us see the next process, mask processing. Mask processing is used to removal of SiO2 layer on the substrate area. On the substrate area. So mask is applied to removal of SiO2 layer. Let us see the diagram. You see the students? Yeah, this one is the bottom layer is a P-type substrate area. Then you can see this one SiO2 layer. Then the third one before you discussed photoresist layer. Here we are applying a mask layer. You see this one, a mask layer. A nickel chroma layer is placed over here above in order to removal of this SiO2 layer. So this is a mask chroma material, and above we are applying UV rays. You see, this is the UV rays which you are applying. The UV rays which you are applying. You see, this is a P-type substrate area, and bottom area. Then second step, SiO2 layer deposition. SiO2 layer deposition. And third step, we are used this photoresist layer. Now this is a mask processing. Mask processing, UV rays applied. UV rays passed through. passed through mask. UV rays passed through mask. Now what happens here in the mask processing? So this is a open area. This is a open area, and this one is a closed area. The remaining is closed area. So this is closed area. This is closed area. This is also closed area. This is also closed area. And this is open area, exposed area. So through this, UV rays passing through this, UV rays passing through this, and below photoresist layer and SiO2 layer affected. You see, below photoresist layer and SiO2 layer affected. So we can, after removal of this mask, then the affected photoresist layer and SiO2 layer can be removed. Then it will be formed as a window in fifth step. So mask processing. What is a mask processing? It is used to removal of SiO2 layer on the substrate area. So the photoresist layer is exposed to the UV rays. This is the open area. UV rays passing through this photoresist layer affected. The bond break in this photoresist layer and SiO2 layer. Then we can remove this one and there is a window formation. So by using this mask processing. The fifth step, you can see active window formation. Active window formation. Active window formation. So you see in the diagram, after removal of mask, there is a window formation. You see in the diagram, the P-type substrate area. After removal of mask, the affected photoresist layer and SiO2 layer can be removed. Now the window is formed. You can see this one. So this is a P-type substrate area. This is a P-type substrate area. Then SiO2 layer here. SiO2 layer here. So the open window. This is the open window formed over here. You see this one. This is the open window formation or active area. We call it is active area or open window. So this is the area, active area for transistor terminals. This is the active area for transistor terminal formation. Transistor terminals formation. Transistor terminal formation. You see this one. So it is an active window formation after doing the mask processing in the fourth step. The next step in NMOS fabrication, thin oxide, you see, thin oxide and polysilicon formation. Polysilicon formation. Polysilicon formation. You see this one. Polysilicon formation. So then in the sixth step, we can entire area deposition with thin oxide and polysilicon formation. You see in the diagram, this is the P-type substrate area and this active window formation. In the fifth step we got. Now you see entire area deposition with thin oxide. It is a 0.1 micrometer thin oxide is deposition, and this thin oxide is act as a dielectric layer from gate to channel. You see this one. So after thin oxide, entire area covered with the thin oxide, then polysilicon is formation. Polysilicon is formation for gate terminal. So this is a p-type substrate area. You see, this is a p-type substrate area. SiO2 layer. This is a thick oxide. The thin oxide, the entire area covered with the thin oxide, 0.1 micrometer thickness. This is a thick oxide, and you see this one is a polysilicon. So backward slashes. So polysilicon. So this is a polysilicon. So this is a polysilicon terminal for a gate. So polysilicon. This is a polysilicon for gate terminal formation. So it is a polysilicon is 1 micrometer thickness. 1 micrometer thickness is deposition on thin oxide thickness. So thin oxide is 0.1 micrometer. Thin oxide is 0.1 micrometer thickness. Thin oxide is zero point 0.1 micrometer. It is act as a dielectric layer. Act as dielectric between gate to channel. Between gate to channel. Gate to channel. Next we can see after polysilicon formation, the seventh step is N plus diffusion. A gate is formed. Then we can form the source and drain terminal. N diffusion for N diffusion for N diffusion for source and drain terminal. Source and drain terminals. Source and drain terminals. Diffuser into the substrate area. Let us see in the diagram. This is a p-type substrate area, and we are seeing the window formation here. You see this one, this is a window formation, and the sixth step after doing the mask processing, we got this. After doing the mask processing in sixth step, we got this seventh one, and we can diffuse here. This part we will do mask processing and then diffusion of n plus diffusion over here. You see this one. So p-type substrate area. This is a p-type substrate area. Thick oxide, and this is a n plus diffusion over here. The forward slashes. The forward slashes. So diagrammatically you can explain in the examination. SiO2 layer, and this is a gate terminal. Backward slashes. Okay. So n plus diffusion. N plus diffusion 4 to 5 micrometer deep. 5 micrometer deep into the substrate area. Into substrate area. Substrate area. How we will do this one? So, and this area heated with high degree temperature here and here, we can diffuse the dopants through this one. We can diffuse the dopants. N plus diffusion dopants diffusing into the source, form as a source and drain terminal. So this is the seventh step. Go for the next step. Eighth one, contact holes. Contact holes formation. Contact holes formation. So required area used for required area for contact contact remaining area covered with SiO2 layer. Remaining area covered with SiO2. Let us see this one, the eighth one diagram. See this one. It is a substrate area. Go for window formation. See this one. This is a thin oxide. Act as a dielectric from gate to channel. Polysilicon. So this area, and before that seventh one we did N plus diffusion over here. N plus diffusion. So this one for contact holes. So only required area can be taken. Remaining is closed with the SiO2 layer. You see this one, and it is closed by SiO2 layer. It is closed by SiO2 layer. We have taken only contact holes. Required area is taken. Okay, this is a P-type substrate area. You can see this is a P-type substrate area. This is SiO2 layer, thick oxide, and this is thick oxide, SiO2 layer, and forward lines for N plus diffusion. This is also N plus diffusion, and this is again SiO2 layer covered, only taken for the contact. This area is for contact holes. Remaining area covered with SiO2 layer. Okay, so what we call this is contact cuts. Contact cut. The eighth step. Next, we can see this, the last step of the fabrication, metallization. Metallization for contact leads. Metallization for conduction. Metallization for contact leads. Metallization for contact leads. So entire area covered with the metal layer, and required area is taken for metal leads, gate, source and drain terminals. You can see this one now. It is a substrate area. Let us see this window, active area. There we can form the source, gate and drain terminals. SiO2 layer, thin oxide, polysilicon. Here we diffused drain and source, N plus diffusion over here. Okay, and this eighth step you are seeing contact cut, contact cut or contact holes. You see this one now. So let us after this, the ninth step is metallization. So here we can cover the entire area with a aluminum layer for conduction. Let us see the representation of a P-type substrate area. P-type substrate area. This is a thick oxide SiO2 layer. This is N plus diffusion over here, source and drain. So this is a thin oxide dielectric layer in between gate and channel. This is a gate terminal, polysilicon, SiO2 layer again. for contact cuts. So this is contact cut ma. This is contact cut. This one is a metallization. This is a metallization. Metal layer is deposited for contact leads. Okay. So metallization. Now here we can take the leads. Here we can take the leads. You see, here we can take the leads. Here we can take the leads. This is a source, gate and drain terminals. You see this one now. So this is a gate terminal, source terminal, and this is a drain terminal. So this is a 1 micrometer thickness metallization. We call it is metallization. This is a metallization. Entire area covered with the 1 micrometer thickness for metal leads, gate, source, and drain terminal formation. So these are the following steps for 9 following steps for fabrication of NMOS transistor. Let me tell you the PMOS fabrication, PMOS fabrication, PMOS fabrication. Steps changes. Steps changes in NMOS. Steps changes in NMOS. Steps changes in NMOS. Remaining all are same. NMOS remaining same. Remaining all same. Remaining all same. So let us see the first step. So in NMOS we can take the p-type substrate area, but here we can take the n-type substrate area. See, listen carefully. N-type substrate area. N-type substrate area. You see this one. N-type substrate area. So it will be like this one. So it is N-type substrate area, backward, forward slashes. Okay, backward, forward slashes, forward, backward slashes. This is the N-type substrate area is taken. So N-type substrate area. The first step is changes. N-type substrate area. N-type substrate area. And also change in seventh step. Change in seventh step. Change in seventh step. Instead of N plus diffusion in NMOS, here we can diffuse P plus diffusion. P plus diffusion. P plus diffusion for source and drain. For source and drain formation. Source and drain terminal formation. Drain terminal formation. You can see the diagram over here. After second, third, fourth, fifth and sixth, it will be same. Now changes in seventh step. You can see this one. The window formation is same. SiO2 layer, thin oxide is same, and polysilicon is same. Polysilicon formation. Here the seventh step is changes. You see this one. The seventh step is changes in NMOS. So what is the seventh step? We can diffuse P plus diffusion. Forward lines with the distance representation. Forward lines with the distance representation is a P plus. So P-type dopants diffused into the substrate area. So this is a backward, forward slashes, N-type substrate area, SiO2 layer, SiO2 layer, and this one thin oxide, and this is a polysilicon. This is polysilicon. This is polysilicon. And remaining 8-9 steps are same. And remaining 8, 9 steps same. So this is about NMOS transistor and the PMOS transistor fabrication process. Thank you.